particularly for those of you who are engaged in industry, you'll probably notice that I have a dual affiliation. I'm a professor at the university, and I'm also a member of the technical staff at Microsoft. And I want to emphasize, and maybe if there's one point to my talk, it is that career position is not a metaphor for the handoff between an academic technology which reaches a point of technology readiness that is then handed off to industry. That is not what's going on. It's not what's going on in the world of quantum computing or in the world more generally of quantum information. And what is going on, in my view, is a cyclic relationship between technology that enables a next step of discovery. The next step of discovery, really into the beyond where we don't know what's going to happen, enables the next step of technology. And the cyclic relationship between, if you want, science and engineering, or technology and education, or academia and industry, is one that I think will propel us into a place that we can dream about. But don't ask me to list exactly what these will be good for, because I want to emphasize that I don't think that that's the right question for now. The quantum computer, the qubit. What could be easier, really? What could be easier than saying I take a bit inside of a computer and I say that it can be a 0 and a 1 at the same time? Well, that sounds kind of empowering, doesn't it? It sounds like you could just have all your bits be 0 and 1 at the same time. It's very simple, and you might think, well, that's the end of the lecture. It's a little bit like, if you wish. That's not what I meant to say. What I meant to say was, you might think that it's a little bit like parallel computing, where you can have the computing going on at the same time. If that were the case, I don't think you would have seen what has happened both in Europe and in the United States with respectively billion euro and 1.3, I think, billion dollar investments in a new technology. That new technology must offer something that extends beyond 0 and 1 at the same time. That wouldn't make sense. And so at least part of what I would like to do today is to try to explain in ways that you will not find confusing. I would say it would be a bit of a disappointment to me. Like Constantine saying he's been in innovation for decades. It would be a little bit of a disappointment for me also to say, boy, that was confusing. That would be an unsuccessful discussion, I would say. But I do want to drill down into why this is not just a 0 and a 1 at the same time, and what it was that Niels Bohr felt that you should be shocked by. Another name that you know, particularly if you are follow the blogs of quantum computing, is a guy named Scott Aronson, who has a similar quote. I think that the spirit of it is rather similar. Quantum mechanics is astonishingly simple once you take the physics out of it. That is, from a mathematical point of view and from manipulating the numbers, it's not that complicated. And so maybe the 0 and 1 at the same time looks good on paper. But it is important to stop and ask, what do we think is the profound difficulty and, relevant for this audience, the profound door that's opening? What door are we about to go through with the emergence of quantum technology? And that's where I want to spend just a minute. On any night, you can stand outside and look up at a star and wonder where that light came from that's now entering into your eye. And if we imagine that light is coming from an atom on that star that relaxed from some excited state to a ground state and light came out of the atom, then you can imagine the light propagating out in all directions, 1 million light years toward me than us, and 1,000,000 light years also in the other direction. And the waves of light emerging from the star give you the impression that someone on another planet on the far side of that star could also perceive that star. But on a given night, I go outside and I open my eye, and the light from the star enters my eye. But we know how the retina works. We know how light is absorbed in the retina. And it doesn't enter the retina like electromagnetic radiation. That doesn't work. That's the discovery of 1900, that light has to enter the eye and enter wholly as a photon. That's what Einstein got the Nobel Prize for, was the so-called photoelectric effect, basically how your retina works. And the idea was that the light coming from the star has to enter your eye as a single particle and trigger the reaction that lets you see it. So that means that the wave coming out is sending individual particles that reach my eye, and I detect them. And when the light hits my eye and I detect that photon, I learn that the photon didn't go the other way. But until I looked, it wasn't determined whether the photon had gone that way, the far side of the star, or toward my eye. So who sends the information out to the far side of the star, 2 billion light years away, that says that photon is no longer available? It's gone into the eye of Charlie Marcus because he went out that night and opened his eye. And you can ask the question, what would have happened had I not gone out that night? Would that photon still be out there on its way in the other direction? Did I, by going out and opening my eye, cause that photon to disappear on the far side of the star? Yeah, I did. And if you're not shocked, then you haven't understood it. You might just think, well, that's wrong. And this notion, which goes by the name of entanglement, and there's many versions of it, is a story that was appreciated in the early decades of the 20th century, and the problem has never gone away. There isn't a simpler story that we've come to appreciate now that explains how it is that by opening my eye, I cause something to happen remotely, a long distance away, or that a correlation appears, is a more technical way to say it. You might even ask, and I think it's appropriate to do so, is that right? Is that really right? And between then and now, the experiments have been done over and over and over again. Here's one from Ronald Hansen, who's sitting with us today. If you want to ask detailed questions, he's sitting right there, and you can ask him about how exactly this experiment worked and why, once again, we must accept the idea that a measurement at one location is correlated with an outcome somewhere else. And how long does it take for the information to propagate from where it was measured to where the correlation appears? Instantaneously. Of course Einstein was bothered. The father of relativity didn't like the idea that a measurement here is correlated with an outcome over there instantaneously. But that's quantum mechanics. And evidently, that's the way the world works. Now we think about computer technology and we ask about one transistor put in a particular state. Let's take that state to be on and off at the same time, our 0 and 1 that was possible at the same time. That transistor lets electricity flow. It flows to the capacitor of another transistor somewhere else and turns that transistor on and, I suppose, off at the same time. That transistor being, say, on, lets electricity flow to a third transistor somewhere on the chip, which charges up and turns off that gate, which then propagates instantly all over the whole chip. Now I measure transistor number 1 somewhere on the chip, and I determine, by opening my eye and looking at it, that it's off. All of a sudden, the fact that it was off the whole time means that the other transistor is off, and the other one is off, and they were all off. How long did the information take to propagate from the detection of the first transistor to all the other transistors on the chip? Same as the time it took for the light to get from the star, instantaneously. I know, you just made that face. You think it's not right. Talk to Ronald, he did the experiment. I know what you're thinking. That's why Niels Bohr said, if you're not shocked, you haven't understood it. So either you're shocked, or you think I'm lying, and his experiment is screwed up, or you're thinking to yourself one of two thoughts, depending on your background. You're either thinking, how have I lived this long without being bothered by this? That's one thought. The other thought you might be having is, how can we use this? What's this good for? And both are interesting questions. The idea of creating such a machine like that chip, in which there is multiple entanglement between the states of all of these, and a measurement here determines an outcome over there, has never existed on this planet, made by this species. Maybe somewhere else it's existed, but not here. And people are trying, and they're trying by various techniques involving superconductors and ions and the angular momentum of an electron, and they're trying all kinds of techniques to create a state in which something can be in an unmeasured state and yet controllable. That's the game that's needed to make one of these machines. Now, we know at the level of Ronald's experiment, when you have two such elements, the original idea of the paradox of Einstein, Podolsky, and Rosen, if you've heard that term, what happens in the outcome? And it agrees with experiment. But what about the multiple entanglement of all of the elements that are interacting with each other? That's never been done. And what will it do? What's it capable of doing? Nobody knows. I would like to spend the rest of my talk making things even harder than that. Let's pretend you've now had 10 years between the last slide and this slide to get used to that idea. And you've accepted, maybe decided you need to go back and get a PhD in this subject, or you just get used to it. But let's take everything that I've said up till now as accepted fact. And what I mean by fact is consistent with every experiment that has been done. There are no experiments that show results that are inconsistent with the crazy story that I just told. And there are countless experiments. Indeed, our understanding of all of the natural phenomena in the universe requires the physics that I talked about. So let me give you 10 years or so to get used to the idea. Now I want to make it more complicated. Because making such a machine will be difficult. The problem with the machine is you don't need a person to open his or her eye. But any interaction of that machine with the environment, any kind of environment, will perform a measurement effectively. It doesn't need to enter a human mind in order to be a measurement. It just needs to interact with the environment. Is there a way to make the information invisible to the environment? That's the second part of the talk. The answer is, we don't know. Theory says yes. Experiment says, let's find out. The metaphor is, if I perform a measurement locally, like I'm a little ant or something crawling on a rope, it's very difficult for that ant to tell whether the rope is tied in a knot. He walks around, he takes a long excursion, and he comes back, and he can't tell whether or not in his excursion he went through and back around, or he didn't. Nature tends to measure in this kind of local way, a local measurement. Will not see whether there's a knot in the system. And so we can ask the question, is there a way to take a quantum mechanical system and tie it in a knot in such a way that local measurement will not disturb the system during the time that operations are going on? And for this, I have to introduce a little bit more physics. Here's the place where, I apologize, you might think I've gone too far. But I'm going to do it anyway. There is, at this restaurant that we live in, 2 items on the menu. They go by the name of fermions and bosons, named after Fermi and Bose. And they have 2 different characters. One is if you take 2 such particles from this menu and you exchange their location, they're so identical that it doesn't count as a different state. The only thing that could happen upon exchanging 2 particles is either the overall quantum mechanical system picks up a minus sign or it doesn't pick up a minus sign. Why a minus sign? Because if we take it and then put it back, you'd like to get the same thing back again, because you just took it and then put it back. That means you can have a minus sign because you do it twice, or you can have no minus sign. And that's true for the 3-dimensional world that we live in. In 2 dimensions, other things can happen. If you lived in a plane, it's possible that the surrounding of one particle by another, which is unambiguous in 2 dimensions, can render the system tied in a knot. It's mathematically possible that evolution in 2 dimensions can remember that a particle surrounded another particle. So the menu of options in 2 dimensions can be richer than just fermions and bosons. I know what I just did. And it's a great time to stop and say, you want me to do that more slowly? 3-dimensional world, 2 items on the menu, lower dimension, other options, because tying things in knots in lower dimensions is unambiguous. We need one more piece of physics, which is superconductivity. I don't need much of it, but I do need one fact of superconductivity, which is that when a wire conducts electricity with 0 dissipation, it does it by pairing electrons together in a mate of 2 electrons. The 2 electrons have opposite angular momentum, and they form a pair. It goes by the name of Cooper pair, named after a guy named Leon Cooper, who was the first one. Think of this in the mid-1950s. And the Cooper pair results in something that can allow electricity to flow without dissipation. In about the year 2000, a theoretical physicist named Alexei Kitaev, working at Caltech and consulting with Microsoft at the time, realized that there were 2 kinds of superconductivity, just like 2 ways to play. What's that game where the music is playing and then the music stops and you have to find a seat? Musical chairs, where you have to sit down. There's 2 ways to play musical chairs when you have to pair up. I'm going to make a variation on musical chairs. When the music stops, you have to find a partner. It's a different game. I don't know what that game is called, but I just made it up. But if music stops, and you have to find a partner. Now, there's 2 ways that those electrons in a row could find a partner. They could find the partner next to them, or they could skip a partner and find the other ones on the other side, leaving 2 unpaired elements at the end of the chain. This is for an even number of electrons within this model. Those are 2 different kinds of superconductivity, and they're characterized by having these unclaimed half pairs sitting at the end of the wire. The theory of that system gave us our first glimpse of what might be a particle in reduced dimension that could be braided around each other and remember. They went by the name of Majorana zero modes, and they were represented by these red balls at the end of the chain. And they contain the remnant information of an unclaimed electron stuck at the ends of a 1-dimensional wire. Now you have to just kind of believe me for a little while. Okay? The papers are rather difficult to read. But the idea is this. I've encoded the information about whether there's an electron or not an electron at the ends of the wire, and the only way that I can find out, just like the only way I can find out whether the photon went to the far side of the star or not, is to bring the 2 Majorana zero modes together and to see what happens to them. Do they become either an electron, E, or do they become a vacuum? marked with an empty box. One of those two things could happen, and those are the two states that we're going to be taking advantage of. Because the Majorana mode is a half an electron stuck at the two ends of the wire, the statistics that we talked about earlier, exchanging two electrons gives you a -1. Now exchanging two Majoranas twice gives you the same -1. But exchanging something twice is like braiding it around each other. Look, there's once, there's twice. So braiding something twice means that the Majorana, when it surrounds, picks up the same -1 that electrons do that made them fermions in the first place. You can now breathe. That's the physics. Not long after these theories were developed, it was recognized by several investigators, including Mike Friedman from Microsoft, that you could make a computer out of this. He and others asked the question, what's this crazy Majorana business good for? And the answer is, you can hide the information about whether an electron is there by separating it. There's no measurement you can do on Majorana number 1 that tells you whether or not, when you bring it together, will it become an electron or not. That's useful. So the theory of quantum computing using this knotted topological structure was born. And as it says in the abstract of this paper, the chief advantage of this, it's called anionic, computation would be physical error correction. As long as they're kept away from each other, they're unmeasurable. And nature won't project that state onto a classical reality. In order to do this kind of braiding, you need to have a branch. If you try to do something like what I just described, which is to flip two of them, you realize anytime you've gone on an airplane and you have to get past the passenger who's coming down the aisle with you, somebody has to step into the row so that the other fellow can go by, and then you can come back in and you can proceed down the row. You need the row in order to get past each other walking down the aisle. And in the same way, in order to compute with Majoranas, you need a branched structure that lets you do that. This will be very important for the material science that's coming up. So the original idea of Friedman and others was to say, make a whole computer out of all of these Majoranas and just move them around each other. And that each time you move them around each other, you can repartner who is with who, and you can change whether or not they fuse into electrons or vacuum. This was originally, for me, very difficult to understand. I couldn't picture how these partnerships would exchange when you moved down the aisle and one went by. And I was in a candy store in Boulder, Colorado, and I saw a machine making taffy, and suddenly watching the machine operate, I realized what would happen when pairs of Majoranas exchanged with each other, and how the original pairing that would be an electron or not an electron would be regrouped when a new Majorana was put in between the two. I stood and watched the machine for a long time, and suddenly braiding of Majoranas made sense to me. This kind of braiding, by the way, if you trace back to the early history of computing, was the first computer. The first computer was a braiding machine. They were the programmable cards that gave the pattern. How do you make them in practice? This is what has occupied our lab, the lab of Leo Kauenhoven in Delft, and several other labs around the world. You combine superconductivity with one-dimensional wires. It requires that you grow the one-dimensional wires. The one-dimensional wires are grown using a semiconductor. Here's what they look like. You grow them using a catalyst in this so-called molecular beam epitaxy machine. You can go to Delft and see a beautiful one there. And those one-dimensional wires, when they're put into the superconductor, will get these red balls at the end, if you want to call it that. They will make these Majorana modes. What do you look for in the experiment? You look for this peak that shows up at 0 when you're in the topological phase. You turn up the magnetic field until the peak appears. And in 2012, the Delft experiment succeeded in producing all of the elements: a superconductor, a one-dimensional wire, you see it up there in the right-hand corner, a normal electron source to inject electrons. And that green circle on the bottom left, bottom right picture shows the emergence of the peak that signals the red ball appearing. Not a dramatic signature, but the kind of thing that inspires the world, that maybe the world is a more complicated place than we thought. It certainly inspired the Nobel Committee in 2016, who recognized, if I may say, the hope of topological materials will be useful for new generations of electronics and superconductors or in future quantum computers. Now you know what they're talking about. They're talking about the ability to make material that has a topological character that can be used for computation. Material science played a very important role in this development. Here's a picture of something which, again, if you haven't seen this picture before, you will find very surprising. The two key elements of the technology are a semiconductor to make the wire and a superconductor, in this case aluminum. And here they are grown together. At the interface, there is perfect atomic registry. That hadn't happened until we tried in Copenhagen to grow that material. And with that technology, let's just say the data began to look an awful lot like what the theory said it should look like. Here are respective data from Copenhagen and Delft Lab, showing really what we were out looking for. So now we have to build a computer out of it. The computer parts get kind of complicated. They live on a chip like any other chip, but down at the heart of that chip is a Majorana device, unlike any kind of technology that's ever existed before. The experiments are beginning to work. I want to say that what's happening in the meantime is new developments in theory. I'm showing you this slide because I think it's funny. You see the bottom, figure 1 of this paper, again, coming out of Microsoft Group, also faculty